Okay, so everything goes well. Hi, everyone. My name is Qingjie Lin. I'm a second-year PhD student at Northwestern University. And today I'm going to present our paper, RobotFlow. It is a data-centric workflow management system for developing the AI-enhanced robots. This work is done with the cooperation with Guoye, Jiayi Wang, Tony Rou, Han Liu at Northwestern University. And let's talk about the classic workflow of AI-enhanced robot first. We summarized the workflow into 4 modules. The first module is data preparation module. This module will transform or encode our data into a state that other module can easily parse. And the second module is algorithm module. This represents the planning process of the robots. And the third module is evaluation module. This evaluates the policy based on a large-scale collected or simulated data. And the last module is deployment module. In this module, we deploy the planning policy into real-world environments. And besides these 4 modules, there are complex interaction with data in this workflow. Like here, the data preparation module will output the data set to the algorithm module. The algorithm module will output the model data to the evaluation module. And the evaluation module and the deployment module will communicate real-time data from simulation or real-world or real robots. And the property of this interacting with massive amount of data make this classic workflow hard to parallelize the development, because like here, the algorithms wait for the data set output from the data preparation, and also the evaluation module should wait for the algorithm module to output the trained model. And there are also one reason for the RobotFlow is that even after we successfully deployed the trained policy into the real world, continuous modification and improvement on each module are still needed when more data get acquired. And so these two motivate us to improve the workflow by propose to design. The first is data-centric design. The second is cloud-based design. So in classic workflow, so besides these 4 modules in the classic workflow, we develop a data engine. And this data engine will abstract out the data set, the model data, the simulation data, the real robot data, and all the 4 modules in this workflow are interacting with this data engine. And the main idea of implementing this data engine is that we leverage the Glassdoor LFS and the roles to expose the data from different sources to the developer. And the developer can access the data from different sources through accessing the storage or visualizing the website or using the API interface to access the data. And besides this data engine design, we have a cloud-based design. We Dockerize each module to increase the maintainability and the reusability. We import each module into a Dockerized container. And in this way, each module can be run as an isolated single process on the system. So this enabled the RobotFlow to develop each module in a parallel fashion. And also, since the Docker can record the change of each module, so it's easier for us to do the version control. And besides this Dockerization, we also introduced the Kubernetes to manage the resource for each module. Like here, each module are wrapped into a Docker container, and then we leverage the Kubernetes to allocate the GPU, CPU, memory resources for each module. And since every module here on the workflow is running on the cloud, So we also provided the graphical user interface for developers to access different modules parallelly. So here is the RoboFlow web GUI. So the configuration page allowed the developer to configure the CPU, memory, GPU source for each module. And the Jupyter Lab page allowed the user to modify the code in each module. And also in the evaluation module, we can monitor the robot behavior in the simulation. We also plot the behavior data from the simulation and let the developer to monitor the robot behavior. And also in the deployment phase, we are able to visualize the image data from the robot and monitor the behavior, the action behavior from the real robot. Yeah, that's all. Thank you.
Thanks very much, Kinji. Okay, so our second talk is from Homanga Bharadwaj, and the title is Auditing Robot Learning for Safety and Compliance During Deployment.
Thank you. Can you see my screen? Perfect.
Yes, we can see your slides.
Okay. So my name is Homanga, and I'm a PhD student at Carnegie Mellon. I'm going to be talking about auditing robot learning for safety and compliance during deployment. So let's start with the problem. The problem is that robots are becoming increasingly good at solving different tasks, often with superhuman precision. We've already seen a few examples of these from the robotics at Google Talk, so I won't go over them again. So given that robots are increasingly good, what exactly is the problem? The problem is that we don't have measures of quantitatively checking whether they're behaving in ways that we want them to. What they're good at doing is optimizing for a certain objective, but what if that objective they're optimizing for is different from that the algorithm designers originally intended? And in the catastrophic limit, what if they optimize for something that is clearly disastrous to humans? So versions of this problem has been proposed over the years, and one of the old quotations from King Midas is that we had better be quite sure that the purpose put into the machine is the purpose we really desire. Now, some familiar examples of catastrophic accidents happening, or maybe not so catastrophic accidents. For example, a robot grasping a cup of water and bringing it over to a person. So the objective is to bring the cup to the person, whereas the intended behavior is to pass it along in a way that the cup doesn't drop or the water doesn't spill on the floor. Some examples from news articles are about self-driving cars that strike pedestrians who are jaywalking, and a Facebook bot that comes up with its own secret language, which clearly it wasn't optimized for. So what is a potential solution for these kind of problems? Well, we could have rigorous testing of failure modes prior to deployment, and we could train the model such that these failures are less likely in the first place, a process we refer to as auditing. The analogy here is to, for example, industry pipelines like car manufacturing, where we have a production phase and a rigorous quality testing phase prior to deployment. Then the question becomes, how do we audit for robot learning? We need to come up with specifications that we want the robot to satisfy under different control variations of the environment and the task. The aim here is to encode preferences about what is safe versus unsafe and what is compliant with human preferences versus uncompliant. To do this, we can't have purely didactic objectives wherein a human specifies a command or an objective function a priori, and the robot needs to optimize for that. This is because humans themselves are usually unsure of their preferences concretely. We cannot come up with a crisp objective function that distills everything we want the robot to be doing. This is true both for imitation learning-based approaches where you have expert demonstrations, or reinforcement learning objectives, reinforcement learning based approaches where we have a reward function as the objective. So the alternative to this is a human in the loop process for learning. This sounds like a natural solution. And based on this, we could come up with the design of an initial auditing framework where we have a pool of human auditors, a bag of objective functions where each objective function is likely imperfect, but there's a whole bunch of them, and a set of tasks or settings where we want the robot to be ultimately deployed in. Then the verification process is for the human auditors to examine temporal sequences of the robot's trajectory and determine whether each trajectory is unsafe or uncompliant. Based on this rating, we can pool this across the human auditors and come up with an aggregate score. Based on verification, we can come up with a verified training phase where you do this verification inside the training loop. In this case, when the auditors determine whether a temporal sequence is unsafe or uncompliant, we swap the objective function with another in the bag. The idea is that each objective function is likely imperfect, but during this iterative process, we could distill human preferences about what behavior is desired from the robot by swapping the function. And we repeat this over training. Finally, the most important phase is deployment, where we tabulate the results of the verification and we release a specification sheet along with the deployed model. This sheet should include the details of all the tasks and settings the robot was evaluated in for auditing and the human auditor scores that was assigned for each task. An example of this for the task we saw earlier could be different tasks could be different shapes of the curb, different types of floor the robot needs to walk in, and so on. The ultimate aim of this framework is to make quantifications of such failure modes in a large number of settings by humans the standard for inclusion in a specification sheet prior to deployment of the trained robot learning algorithms. In summary, my main aim was to bring ideas from the AI alignment community about objective misalignment into the robot learning community and try to formalize the necessity for auditing. The framework that I described is definitely not practical for implementation as is, but we as a community should probably think about ways you could develop and implement mechanisms for auditing robot learning systems before deployment. Do shoot me an email if you have any thoughts or follow-up points. Thank you.
Our next talk is going to be given by Sergey Levin from UC Berkeley, and the talk is titled Understanding the World Through Action.
All right. So why does deep learning work at a very high level? Well, if you have a very large model and a large data set, then you can get learned models that generalize very well. But of course, conventionally, the data set needs to be labeled, and that's where a lot of trouble comes in, that we need to obtain these large labeled data sets. And a big reason for the explosive growth in self-supervised learning recently is that with self-supervised learning, in principle, you could have a smaller labeled data set and a giant unlabeled data set of this kind of low quality garbage data that you can just find off the internet. And self-supervised learning allows you to incorporate that. And that's grown tremendously in NLP and computer vision and other fields. But what do these techniques actually learn from? Where do they get their knowledge? The classic view is, well, maybe we're doing unsupervised learning. We have some kind of density estimation problem. That's great because it's purely data-driven. It's principled. You can do lots of math in your papers. But ultimately, it's just learning from whoever collected the data. So if you have a classic static data set like ImageNet, which was collected by Flickr users, you're learning from whoever chose to photograph the things and put it on Flickr. If you're learning from garbage data off the internet, then you're learning from whoever threw out their garbage, and that doesn't sound very appealing. Indeed, this is not actually the recipe that ended up working so well. The current most popular approaches to self-supervised learning are all based around some version of data augmentation, which works really well, has much less math, but you're learning from the smart researcher who designed those data augmentation rules. So that also doesn't seem so appealing because really the knowledge is just put in there by another engineer. Stepping back a little bit, if we want to design a more principled approach to large-scale self-supervised learning, we could start by asking, why do we need machine learning anyway? And we could start with an even more basic question, why do we need brains? Let's ask Professor Daniel Walpert. He's a world expert on brains, and he has this to say. We have a brain for one reason and one reason only, and that's to produce adaptable and complex movements. Movement is the only way we have of affecting the world around us. I believe that to understand movement is to understand the whole brain. I would put forward a postulate about machine learning inspired by this. Perhaps we need machine learning for one reason and one reason only, and that's to produce adaptable and complex decisions. Let me try to defend this postulate. For all of us here, we work on robotics. In that context, it's fairly clear how our learned models output decisions. Your robots will decide how to move their joints or how to steer a car. But even if we're thinking about things like image classifiers, they also make decisions. Their decision is not the image label. It's actually the thing that happens afterwards. So if you have your system running for a website that will tag users' photos, the decision might have implications about how the user then interacts with that system, whether they're happy with that interaction, and so on. So all these outputs, even for supervised learning systems, are decisions, and they have consequences in the real world. So what if we think about a self-supervised learning framework that is rooted in decision-making? The basic principle is that if the goal is to eventually make decisions, let's pre-train the models to be good at making decisions. A decision, you can think of that as an action that leads to some outcome. So what if we learn how to take actions to produce any possible outcome? If the point of machine learning is to make decisions, this seems like a great recipe for pre-training. This is essentially a goal-conditioned or task-conditioned reinforcement learning problem. So you could have your agent essentially playing in the garbage dump, learning about how the world works. The problem is that with naive RL, this is a very costly interactive process if done in the real world. It kind of defeats the point. We want to gather all this garbage data that's already available, not introduce another costly online learning loop. So if self-supervised learning is about cheap data, this somewhat defeats the point. So that's why we need the second part. We need to bring in offline reinforcement learning, which can leverage data that is already there, but then use it for this self-supervised reinforcement learning process to learn how to make decisions. So let's learn to make all possible decisions using offline RL from plentiful data that we've already collected, and use this as universal pre-training to help us make other task-directed decisions for downstream tasks. So the recipe is you take your low-quality data, which could be all the data from past interactions your agent has had, use it for self-supervised reinforcement learning, like goal-conditioned RL, and then use this to learn downstream tasks. And remember, this doesn't have to be a downstream RL task. It could actually be a downstream classification task. So really quickly, an example of something that gets at this point in some of our recent work. This is a paper by Yevgen Chebatar called Actionable Models. This is a goal-conditioned robotic manipulation system. So there's no reward function. The goal is just to match a goal image. It's going to use offline RL, CQL in this case, and train entirely on prior data that we had collected for other previous projects. Now, the resulting system is good at matching goal images, but that's kind of not the point. The point is that then we can use it for downstream tasks, almost like a robotics version of BERT. So you train with your self-supervised objective to accomplish goals, and then you can fine-tune with a task reward. In reality, it's a joint training process, not a pre-training process, but that's kind of a detail. And then it accelerates downstream tasks. So just to conclude, this is not just about robotics. Self-supervised offline RL can be applied to any domain where we need machine learning to make decisions. And there's lots of missing pieces left to figure out. What's the right self-supervised objective, the best algorithm? How do you transfer to downstream tasks, utilize diverse data sources, et cetera? But if we can figure out these questions, we can develop powerful and principled self-supervised learning methods that will prepare our learned models for precisely the thing we need them to do most, make intelligent and adaptable decisions in the real world. Thank you.
Our next and final talk for this session is going to be given by Vika Antonova. And her talk is titled Learning to be Multimodal, Co-Evolving Sensory Modalities and Sensor Properties.
All right, hello. I'm wondering whether the slides are showing up yet. Not yet?
Yes, yeah, yes. There's a little bit of delay, but they're going to
okay. Yeah. All right, let me try to set it up here. Okay, so yes, we're going to talk about learning to be multimodal. And if we look at the impressive variety of sensors that animals have evolved in nature, we see vision beyond the visible light spectrum, perception for a wide range of sound frequencies. Some animals use electroreception for underwater localization, and some birds even figured out how to use Earth's magnetic field to do long distance navigation. So if more is better were the main law of sensing, then we would see an impressive agglomeration of sensory capabilities in the more advanced animals, such as us humans. But instead, we see that sensors are specialized, and our guess is that sensor choices co-evolved with the organisms and were subject to the constraints of energy, size, and the target tasks. And likewise, in robotics, we face the need to select a subset of sensors to address the budget size and energy constraints, but it is difficult to select the subset because we, these days, need to look at what the downstream learning methods are basically getting from the sensor data, and that determines what is necessary and sufficient. And another note is that using high-dimensional sensor data is not suitable in all cases. We might have tight energy constraints, we might have compute bandwidth and storage limitations. So sometimes we need smart hardware that is capable of targeting sensing and selecting the kind of a way to compress the sensor data. So making a single sensory modality precise and robust to get a human level performance and autonomy, that could be very expensive or even intractable. And so a promising direction is to use multiple sensory modalities, but it is very easy to settle into a local optimum of just using a common existing generic combination. And another issue is that we usually in this view treat the sensor properties as fixed, something that is just given by the manufacturer. So our main idea here is to co-evolve the sensor hardware design and the choice of the sensory modalities together with the learning methods that use the sensor data to solve a set of target tasks. So how can we do this? We can start by sampling a batch of sensory modalities, for example, vision and touch here, and then sample their sensor properties, for example, low resolution vision and high resolution tactile array. Then we can train to solve a set of target tasks and infer the utility of the combination of the sensor based on the task performance. And then we can maintain a global posterior that models utility of various sensor combinations and use this some data efficient approaches like Bayesian optimization, for example, to select the most promising candidate to try next, and so on and so forth. So updating the hardware design on each iteration, that would be very expensive. So we can instead start by creating approximate models of various sensors in simulation and then feed the synthetic data to the learning methods and update the posterior, then update the sensor design, the simulated sensor design, and so on. We can also use hardware data, so collect data from real sensors that are expensive, for example, high-speed cameras, high-resolution tactile array, and then subsample the signal to identify the maximum level of degradation that is still acceptable to solve the tasks. So about 10 years ago, it was shown that high-speed vision and actuation allows to solve very challenging tasks such as dynamic cloth folding and in-the-air knot tying. But the hardware that is used for this is not widely adopted for solving these tasks. So what can we do? We can identify maybe a lower frame rate is sufficient and lower the cost. We can also experiment with different predictive methods to see if the high-speed control can be replaced. Another thing that we can do is we can experiment with skin sensors, for example, infer the optimal coverage of the skin for the robot's body for various areas, and also understand what sensitivity is necessary, and also explore with data compression methods. And it is useful to note that combining vision and tactile and other sensors can be done effectively even with low-cost solution. For example, here, an exploratory hand can allow us to estimate object properties with minimal object displacement. We can also combine various sensors to get robustness against external forces, perturbations, movement of the target, and even camera occlusions. And so overall, we note that there are some immediate benefits of lowering the costs and finding optimal combinations of sensors to solve a given task, and also long-term effects where we can guide the research and development with this overall co-evolution approach. All right, thank you.
Okay, so I said before the session started that it would be interesting to see if anybody can come up with any common themes across all the 4 talks. So does anybody have any brave ideas as to what those themes might be? So one of the themes that I thought was consistent across, certainly in the first 3 talks, was the issue of scalability. How can we actually design a system that in some way scales either with using pre-training on offline data sets, or modularizing a workflow, or using people in the wild to label data sets. So there was a common theme there. And I was wondering about Rika's talk. So how, with this scalability idea in mind, how perpetual do you think this kind of co-design of sensors and using machine learning to design sensors, how perpetual do you think that could be? Could it be done autonomously, or would there always need to be a human in the loop? And if there needs to be a human in the loop, would that then actually be better than the human just designing those sensors using their own brain rather than the machine learning brain?
Yeah, that's like an interesting next step, right? We think that the sensor design involves the human in the loop, at least when you're doing the hardware modifications. And for example, right now, if we're doing co-design of morphological changes, right, then somebody needs to go and 3D print this, right? And for the sensor design, we think that it would be even more kind of like human knowledge and priors involved, because like some hardware engineer would need to go and wire something, make the new blueprint and so on. So yeah, I guess that's the next step to figure out how to autonomously evolve the hardware design so that the system itself can update everything along with the hardware. So that would be interesting. Then that would be really scalable, yes. And for now, you're right. I think in this co-evolution design, the one bottleneck could be that, all right, you can do a lot of things in simulation, right? Everything is scalable. You know, we can do massive compute, but after you're actually decided, okay, now I will update my hardware sensor, then yeah, there needs to be some sort of a human engineer in the loop to do this. So yeah, that's a good point, good next step, I think.
So do you think, like, building upon that idea, do you think, if you're just developing new algorithms and testing them out in simulation, then you're kind of safe that that's just going to be an algorithm developed inside the computer. But if you're actually, if the hardware itself is evolving, are you worried that you'll turn up one day and a monster has appeared that you were not predicting?
So the thing here to note is that, for example, the way that we thought about this co-design is this is co-evolving with the learning methods that we choose and the target tasks that we choose. And so here, I think we are bringing the point back home to saying, if we have designed the loss for the task to be correct, then ultimately this whole system is going to evolve to solve these tasks. And of course, if we observe some of the artifacts like what we kind of see in RL, where we specify the task and then some sort of behavior arises that we didn't expect, then this precisely would be kind of the point where the difficulties would arise. But the hardware itself here, since it's for sensing, it doesn't seem like that is the big danger here, because it's less for changing actions or changing embodiment of the agent, but it's more for changing what the agent is perceiving. So I would say that this particular line of work is a little bit safer. But again, now here, since it's targeting at solving these tasks, if the tasks objectives are misspecified, then we would basically have a better system for solving these tasks. And yeah, we have to agree with the reward or the objective function for these set of tasks.
Yeah, so it's up to us as the engineers to limit what can evolve autonomously and what cannot. I guess that relates back to the talk on auditing. I guess you could bring in, you could have humans watching the sensors evolve and then saying, okay, stop there because that's going to become dangerous if it continues evolving in that way. Yeah. So let's see, Marco, are there any questions on feed loop or any thoughts on any of the themes that have emerged?
Yeah, there is a question from Andrew at Johns Hopkins University. And the question is as follows. With this co-evolution concept, what about accounting for human diversity, such as disabilities?
What about accounting for it?
Yeah.
Is that the question?
Yes.
So I think the good part, of course, is since we are hopefully going to be lowering costs in many different areas, that usually is something that is key to addressing, for example, people with disabilities or certain groups of people who maybe have characteristics that are not extremely common. And I think this is one of the enabling powers here. One of my most favorite examples is the Open Hand project. I think this is the name, I'm not entirely sure, but basically what they're doing is they're trying to have open source designs for prosthetic hands. And that allows to bring the costs down dramatically, and also allows the users themselves to evolve a little bit, basically customize the hardware based on what they need. Because the design is accessible, they can do it kind of personalized to what it is they need in their family, in their situation. So I think this is one of the key areas where this could really help, that you, instead of having just the standard sensors that address very, very standard situations, you can have a range of sensors that address very particular situations, and they can be targeted a bit better to the individual situation.
Thank you.
All right, any questions from people in London, or any general thoughts? Ivan.
Hi, so thanks everybody for your talks. This is a question mainly for Sergey. So I'm wondering about your view on the issue of how much of the robot learning process should happen in the lab versus in the user's environment after the robot is deployed. Because if you're focusing on unsupervised learning, as you talked about, then that opens up the opportunity of doing both without putting too much of a burden on the user, right?
Yeah, that's a good comment. And I think that's exactly right. So basically, I think a big part of the promise of techniques like this is that you actually don't have to be very picky about getting just the right data, but rather switch into a mode where you're using any data that you have available. And I think that, the ideal thing is actually a kind of virtuous cycle where it's not about selecting between data in the lab or data from deployments, but actually, getting the best system you can, deploying it, then getting data from deployment. But the other thing is that I think that self-supervised reinforcement learning methods, if set up correctly, they don't even have to rely entirely on data collected by your robotic system. It can be any data that is structured appropriately, sequential data where there's some notion of intervention that can be treated as action. So in some domains, this is obvious. So if you have, for example, dash cam videos of people driving cars, you can extract some notion of action from changes in global direction. Conceivably, you could even figure out how to do that from YouTube videos, as long as you have something that you can label as an intervention or action for the algorithm to reason over. It doesn't have to be a real action, it could be a virtual one. So I think in that sense, it should be possible to do this with very broad sources of data, including ones that are far outside the lab. But of course, to my knowledge, that hasn't really been done yet, so this is very speculative.
Jackie, yeah.
Hi, thanks for all these talks. It was great. I have two questions. Is that okay?
Yeah,
okay.
Sure.
The first one is sort of like a comment about Sergey's presentation on the actionable models. I think that it's actually a bit of a generalization to say that the difference between fine-tuning from like a pre-trained representation versus joint optimization is the same. Like it really would make a difference in deployment if you're like shipping a pre-trained representation to like many different robots who are doing different tasks.
Yeah, I agree with that. Yeah. I think it would be much better if it was pre-training and more scalable. But I think there's, the distinction there is between, the verifying that it's scalable and verifying that there's even knowledge to be transferred. So I would view that as an experiment that confirms that there is something to transfer. As to how to do it, I think that's still very much an open problem. And I agree with you on that.
And my second question is sort of, I think, for all the speakers, but like Rika specified like Bayesian optimization and GPs, probably because that's her specialty. But I guess that, that speaks to scale, like the amount of data you have. And Bayesian optimization makes sense in this case of coevolution of hardware, because you might have like very little data and collecting that is expensive. You can also make these simulators, but then there, like, I think often, like, and also like a lot of what like Sergey's work is in deep learning at a huge scale, right? So how do you reconcile this? Do the other speakers have opinions on techniques and with what they're trying to accomplish?
I could make a comment here. I guess one of the issues with learning from large data is related to what I spoke about. So it's very difficult to regulate about the behaviors that emerge from the algorithms. So that could be something, I guess, to think about how do we inject useful priors to the models in addition to self-supervised reinforcement learning, for example, from large data. So I guess that's just one of the comments about that. Curious if you have thoughts about that. Yeah.
I can also make a comment. So right now we can scale GPs pretty well. Still, neural nets, various versions of them are maybe arguably more scalable. But I think the reason why I brought up specifically Bayesian optimization there and GPs is because we have uncertainty estimates there. And so in that case, it wasn't only about the data efficiency, but it was also about the fact that if we want to make a change in the real world, if let's say we learn from simulation or from some pre-collected data that we sparsify, then we want to sort of be somehow certain that it is worth doing this change. It is worth investing time and resources into doing that. And so I think any model, if we want to scale it up, let's say with some neural nets, maybe Bayesian neural nets, maybe some ensemble approaches, something that can estimate uncertainty for us, that brings additional benefits. So one is we maybe are now sure that it is something that is worth looking at because we have collected enough data. And another thing is that we have kind of a more global view of what is happening overall because we have uncertainty estimates from various kind of parts of the space as opposed to just looking at one particular guess. Okay, this is the one thing that maybe we are after. So that's how the GPs came into the play, because previously they have been sort of the standard for getting good uncertainty estimates. And right now they're pretty scalable, although there are other competing approaches that could be neural net based that also offer this functionality.
Okay, Marco, how are things in the virtual world? Do you have any questions?
We do have a new question. So this question is from Hermano at Dyson Technologies. The question is as follows. Still in the direction of scalability and perhaps practical considerations for concrete domestic applications, I was curious of what are your thoughts on how we could also take into account uncertainty in model predictions and or auto-distribution scenarios in order to bootstrap continuous improvement of learned robotic skills. So it's basically a question about how we can account for uncertainty in model predictions and auto-distribution scenarios to bootstrap improvement in learned skills. Any takers?
I think I've already argued for using models that can estimate uncertainty. I would say, and I would maybe ask other speakers to comment on that, the challenge that we have right now, I think we all agree that, oh yes, having uncertainty estimates is good, but especially in the times where we're doing a lot of things with neural nets and we're doing a lot of things with various approximations, we have developed a lot of techniques that can return uncertainty estimates, but I think we haven't fully analyzed how good those uncertainty estimates are. And so I think this is like one of the major challenges right now, that the analysis of, because we are scaling, right? We can't anymore look at the small toy examples that we can fully kind of comprehend what the outcomes here should be. And so we get some uncertainty estimates and we don't necessarily evaluate their quality in practice. And so we might not know, this auto-distribution performance, for example. We might say, oh yes, I can do this because my model is more sophisticated and I can sort of say something interesting about it. But can we actually, do we have enough in terms of doing this analysis? And maybe in your view, what are the next steps for us to be able to get more of this?
Yes, I think this is a great point. The point of calibration of uncertainties is something that is critical for many applications.
I can maybe comment on that a little bit. This might be a little too much in the weeds, but in regard to scalable uncertainty estimates with deep nets, I think one important factor, one important consideration to have is that typically we don't actually need uncertainty. We need whatever comes afterwards, which would be an upper confidence bound or lower confidence bound or something like that. And oftentimes it's actually a lot more scalable with large models to just directly learn that thing instead of learning a full posterior. Certainly in reinforcement learning, we've seen that in both exploration and offline RL. In exploration, it's a lot easier to get upper confidence bounds with bonuses, and in offline RL, it's a lot easier to get lower confidence bounds with some kind of pessimistic method. So for anyone who's frustrated about how difficult it is to train Bayesian neural nets, what I would suggest is to consider what you want to actually do with the uncertainty and just directly learn the thing you ultimately need.
I wanted to add a bit to the part about exploration that the question mentioned. So when the robot is trained, for example, in a domain and it needs to collect data in an out of distribution setting, then one of the challenges could be that we don't even have a good policy to start exploration in that domain to collect useful data. And this is where I guess the thing about unsupervised pre-training that Sergey mentioned could really help, because that could help us get some useful initial policy, for example, even in the out of distribution domain. And the robot could start from there in order to collect more data. So I guess that is one of the ways of ensuring that the data collected in the out of distribution domain is not completely garbage and so on. And that could actually help in bootstrapping the learning of the robot.
And I do have a question for Sergey. So my question is, the paradigm that you have discussed is of course general and in principle applicable to any sequential decision-making problem. I was wondering if you have any insights on some specific application domains where you think it might be more feasible or promising to apply this paradigm to.
Yeah, so I think I can certainly speculate about specifics, but I want to also, maybe elaborate a little bit on why I think it's general. It's, I gave an example of this stuff doing something sensible in robotics context, but I think actually the big promise is, we often think about pre-training on other settings, making robotic learning better in that way. But we could think about the opposite. How can interaction data that an autonomous system, like a robot or an autonomous car gathers, how can that be useful for other machine learning applications? I think that's actually, that's also a really fascinating area where this can make a big difference. Maybe we could in the future, instead of thinking about pre-training on ImageNet to make our robots better, think about pre-training on robots to make ImageNet classification better. And insofar as the purpose of these machine learning systems is to make decisions, perhaps pre-training them with ways that teach them to make better decisions will actually make them better at other tasks, better at reasoning about the actual consequences and the actual causal factors of variation and things like that because of the way that they were pre-trained. So I think that actually that kind of stuff is one of the more interesting hypotheses that could be explored in the future, to say like, well, can learning with an aim towards decision making make you better at picking up on causal factors for downstream tasks that are not necessarily explicitly reinforcement learning tasks. So I would be very curious to see if that pans out.
And I also have a question for Homanga about the auditing framework proposed. I think it's very interesting and perhaps really needed, for example, for safety critical applications. But I was wondering if you have any insights on how this auditing approach would work in those settings where a mistake might have detrimental consequences. For example, in the case of an autonomous car, a mistake could be a collision that could lead to an injury. How would you tailor or apply your forensic approach to those types of safety critical scenarios?
Right. I guess in those settings, we would not sort of wait for the auditors to assess when a failure has occurred, for example, but to assess that a failure is likely to occur. For example, in the self-driving car, if a human is sitting inside the car and a failure is sort of likely, for example, the car is likely to drift out of the road or is likely to collide, for example, then the human auditor could sound a bell and maybe take over control of the car and record that as a failure of the robot in that particular setting. So in very high stakes applications, obviously this is kind of challenging, but that could be one of the ways of assessing the capabilities of the car in terms of auditing. So not wait for a failure to occur, but assess impending failure, essentially. And because a human is doing that, so that might be easier to do it compared to assessing it automatically. Yeah. Does that answer your question?
Yes, it does. Of course, this assumes that you have enough control authority to basically stop your system before something bad really happens.
Yeah.
Okay, do we have any questions here in London? Yeah.
Yeah, I have a question for Sergey. So how do you see online learning in your framework? So like if you have the robot pre-trained, it's pretty good, but maybe it does certain mistakes, but then it would continue these mistakes all along because it wouldn't sort of learn from the current like experience. Do you see this problem, or how would you circumvent it?
Yeah, I think that's a very good comment, and certainly I wouldn't view this as being in exclusion to online learning. I think the point is rather that in the same way that self-supervised learning now gives us a good starting point, the point is to get that good starting point. So in the example that I showed from Yevgen's paper on actionable models, he wasn't, the point was not just to take a model that was pre-trained on goal reaching and just directly use it to do stuff. The point was to then combine it with a downstream task objective, and that did employ online learning. So I think that's basically the right recipe, is to get this basis for generalization, this foundation to build on from plentiful prior data. And then once you've got that foundation, then you can more rapidly and effectively acquire a task. And that task should also generalize better because you have the right representations to work with. So this is not to the exclusion of online learning. It's just to essentially bootstrap it more effectively.
So I have a question for Kinji and also Sergey. So Kinji, in your proposed framework, you have this modular idea where evaluation and deployment are treated differently. So on this theme of scalability, do you think that is limiting in that you wouldn't then be using the deployment data to train the robots? And then Sergey, a follow-up question is, where do you see this fine-tuning in terms of this modular pipeline? Would you see it as part of evaluation, or would you see it as part of deployment? So for example, would you be comfortable selling a robot to a factory and then that robot fine-tuning in that factory itself as part of the deployment, or would you only want to do that fine-tuning inside the lab? So Kinji, perhaps you can start this.
Yep, that's a good question. So I think for your questions, I would say our data-centric design, our proposed data engine, make it possible for the algorithm, for the policy to be continuously developed from the data, not only from the simulation, but also from the real robot. Our data engine, including the data from the simulation, also when we are deploying the robot, the data engine also will expose the robot from the data from the real robot. In that case, the algorithm module and the evaluation module had access to the data engine. So in these ways, we are able, in our workflow, the data engine propose, so make it possible for the evaluation module, algorithm module to continuously develop the model from the data.
Yes, so Sergey, if your fine-tuning was part of the deployment, would that make you comfortable, or would you want that to be only done in the lab?
Yeah, that's a good question. So I guess I have a boring technical answer and then maybe a more controversial, more speculative answer. So the boring technical answer is, well, in some ways it comes down to an empirical choice, like, is it better to do joint training or fine tuning or whatever? They both have pros and cons in various ways, and it'll probably be whatever works best. But in regard to, would I be comfortable? There's something loaded in that question. To kind of get at the spirit of what you're asking, I think actually a system with appropriate pre-training should make us much more comfortable than a system that is learning from scratch. Because besides learning a good foundation, a good representation, you should also figure out which kinds of behaviors are more reasonable and which kinds of behaviors are less reasonable. So if you pre-train on a lot of data of various drivers driving around, well, you should at least figure out some basics like, suddenly driving into a concrete wall is just not something that happens a lot in the data. It's not something that you can make reasonable counterfactual inferences about. So you probably should not do that, all else being equal. It's certainly not a ironclad method for safety. It's not like addressing the stuff that Hamanga discussed. But I think in the balance, a pre-trained system should be better and we should be more comfortable with it than one that is not pre-trained.
Yeah, so it's all about how, it improves your comfort, but it's difficult to say absolutely where that cutoff is. So we have time for couple more questions, I think. Yeah, one here.
And there is also one more question from the.
Yeah, Marco, I'll go back to you in a moment for the final question.
Yeah, this is also for Sergey and the idea of self-supervision from large amounts of data. So from what I know from the GPT-3 work, they said that they had to filter out their large-scale text corpus to make it work properly. So I was curious whether you thought for the applications in robotics or in general, really, how important it is to filter out or clean out the data, even though it's been used only for pre-training.
That's a really great question. Since this is the blue sky session, I feel like that kind of gives me license to just like make some stuff up without needing to substantiate it with evidence. So I'll make something up, but I'll preface this by saying this might be nonsense. My answer here would be the following. I think this should be much more of a problem for generative methods like GPT than for a method that trains for decision making. And the reason is that a language model learns to do what was done in the data. So it becomes very important then what the distribution of data is. Remember at the beginning of my talk, I talk about this P of X, right? Unsupervised learning learns P of X, so it's learning from whoever collected that data. And there's a really big difference between that and learning to make decisions. When you're learning to make decisions, you're really asking counterfactuals. What would have happened if I did something else? And I think that might actually end up being a huge difference in practice. And it might, and this is the really speculative part, I don't have any evidence to substantiate this, it might actually make you more resilient to including bad data, because when you include bad data to the decision-making system, it is evidence that bad stuff could happen, that undesirable things could take place. To GPT, it's evidence that this is something you should do, because that's what you're training, that's how you're training the model. But again, I just want to make it clear that I don't have any evidence to back this up.
Thanks, Sergey. So Marco, would you like to ask the final question?
Sure, a question again for Sergey. What unsupervised reward formulations do you find most promising? And what is a good measure for being a good unsupervised reward?
Sorry, was that a question for me?
Yes.
Okay. I think that's a really important open question, actually. So, there's some easy answers like we should do goal reaching, but I find that a little unsatisfying because there isn't any seemingly fundamental reason why that should be the case. There are also much more elegant methods for unsupervised skill discovery that take a more information theoretic approach to the problem. And we actually have some recent work led by Benjamin Eisenbach from CMU that analyzes some of the theoretical properties of these things. But from a practical standpoint, so far those methods have been a little tougher to get to work well. So I think in general, this is a really interesting open problem. And for those of you that are interested in this stuff, I would encourage you to work on that because I think there's probably some pretty cool things that you can discover in the next year or two there.
And one more question since we have still 1 minute left. Again for Sergey, do you think the large data set, the pre-training model will restrict the creativity of the policy? And the argument is that since training from scratch could lead to a policy that has never existed in human experience, but it's also useful for the task.
That's a great question, actually. Yeah, I think, my first instinct was that I need to defend the thing I presented. But actually, I think there's a point there. And it is true that if you use prior data, especially data that came from humans, you are sort of loading the model up with that prior, and it will probably cause it to do things that are more similar to that. So yeah, I guess you could imagine that if there's some task where you want like a totally novel solution, it's better to start from scratch. I guess like the classic advice that sometimes is given to starting PhD students is like, you should read papers, but don't read like too many papers because you want to still like come up with original ideas. Yeah. And maybe that's true for our robots tutor degree. So I think there's a point to that.
Thank you.
All right, so it's 3:30 here in London, so I think we should draw to an end here in the Blue Sky session. Thanks so much to all 4 speakers for joining us.